All right, gang, math 6610. Going to dive into an ANCOVA example. The purpose here, I'm going to look at how we test assumptions, how we calculate effect size. We're going to use G-power. What else am I going to do? I'm going to run the ANCOVA design. So that's kind of where we're headed here. So let's grab some data from the desktop. You will have access to this. So there's the data set I want. See if I can drop that right in the middle so it works. All right, let's look at the first few cases. Now, what's going on here? This is actually a data set that I collected. I'd say it's probably small. Let's just grab one of them. So 51. So this is one of my intro stat classes, Stat 1150. I taught, it's been a while ago because we no longer call it 1500, we call it 1150. So I would assume probably 6 or 7 years ago. And so we have the ACT score, we have the final exam score, and we have the group. So if I want to examine a few things here, I would overall, the mean ACT for the 51 students was about a 21.5. Let's see what the final exam score was, 72, so decent. Now, thinking ahead in terms of running an ANCOVA, I know that my group, and what happened here, let me explain the group. First thing I need is to convert group to a factor because it's given in zeros, ones. I'll tell you what, let's take take a look at that. All right, so there were 17 students. If I recall correctly, group was this. A 0 was taught with my stat lab only and a TI 84. 1 was taught with my stat lab and StatCrunch. And 2, I think, was, well, no, I don't think, I know, was taught with my stat lab and R. So the main thing that we're looking at here is we're teaching my stat lab was irrelevant because it's included in all. So it was the technology that I used to teach the class, whether it's a graphic calculator, StatCrunch, which is a really cool statistical software package that is included in my stat lab, or R, which we're using right here. So the first thing I see is that my group factor, which is my independent variable for an Anova and ultimately ANCOVA design, is not a factor. So I can check that by is factor, and I will get false. So I need to convert it to a factor. So I'm going to rename it. So from here on out, when I use group, which is the instructional unit, we'll need to use F group. And I'm going to set it as a factor. So I said set it as, it is group. So now you can see if I do is factor F group, it'll say true. So that's what I need because again, for ANCOVA, well, Anova, I need what? A dependent quantitative variable, an independent variable that's categorical. And when I transition into ANCOVA, I need a covariate that's quantitative. So what I'm going to have here is my dependent variable is going to be equal to the final exam score. My independent variable is now going to be F group because it's where I have factor. And my covariate is going to be the ACT math subscore. So I want to see controlling for entering achievement level, which I've measured using the ACT math subscore. I want to see if there's any difference in final exam score. All right, so we're off and running, right? So the first thing I would want to do, and I hope that I impressed upon you enough in the previous video, but the first thing I want to do is just take a look at the straightforward Anova. So I'm just going to call this my base model. and I'll run an AOV of final over group. Now, guys, be careful there because it's going to be so tempting to just use group, right? But it's not a factor, and it'll give you some wacky results. All right, so my base model, and I see that I do not have statistical significance. So what I can determine from that is that taking any consideration of the covariate, the beginning achievement level, there is no statistical significant, the means are not statistically significant different. There is not a statistically significant difference in means for final exam score across instructional unit. Now, in transitioning to ANCOVA, I would want to test my assumptions. So I think the first thing I'll test is the normality assumption. So I think the easiest way to do that is to grab the GGPUBR package, and then I want to run the GGQQ plot, and I want my base model residuals. Really nice because it gives me my 95% confidence band. So I'm looking to see if there are any points outside the gray area. You may say that points outside the gray area, but that's only a limitation of graphing. It's clearly within this bound. So I have no concern based on this plot that I've violated the normality assumption. But you know, we love p-values, don't we? So let's grab a p-value. What's up with this? Oh, I'm on autopilot, ladies and gentlemen. Well, I'm on autopilot, but I can't spell. Okay, so the Shapiro test, remember the null hypothesis is we can assume normality. The alternative hypothesis is we cannot assume normality. And since our p-value is greater than 0.05, we can check the box of the normality assumption. Next thing I want to do is check equal variances. So I think the plot base model 1 gives me a nice visualization, right? So I have 3 groups. So seems to be a little bit more variance in group 1 than in variance 2 or group 2. And the variance in group 3 seems about similar, right? So again, this would be a good plot to include when discussing the equal variance assumption. But as we know, let's go grab the, wow, the package car, so we can run. Well, ladies and gentlemen, I am having a hard time with typing today. So we'll run the Levine test of our final over our factor group, and we squeeze right in there, right, at 0.0531, so we can assume equal variances. Now, the next thing I want to do is I want you to install a package called Tidyverse. I've already installed it, so I'm not going to install it again. I'm just going to access the library and then just recall, in case some of you haven't been watching the videos, as you should. If I want to install the package, install it this way, but I don't need that because I've already installed it. So all I need to do is just access the library. All right. Now, once I do that, the next step is to dive into the homogeneity of regression slopes. And I'm going to show you two different ways. The first way is just going to be, well, kind of like what we did with the normality assumption. We're going to look at a picture, look at a graph, and then we're going to calculate some p-values. So the very first thing I would do is I would want to, now remember, homogeneity of regression slope says what? It says that if we look at the slopes of the dependent variable over the covariate, that we would expect the slopes to be approximately the same for each of the groups in our independent variable. So we're going to do that. I'm just going to call it plot because I'm not that creative. And I'll use what's called a ggplot command. The first thing I want to do is define which data set I'm using. So I'm going to use base data, I believe is what I called it. No, I just called it data. Getting it confused with base model. All right, and then I'm going to use standard procedures. So it's AES. First thing I want to put in is my covariate, which is ACT, because that's going to go on the horizontal axis. On the vertical axis, I want my final exam score. But then I want to provide different lines for F group. All right, then I'm going to, let's see, what do I want to do next? I want to go in and put plot the points. Actually, that should just be point, I believe. And then I want to create my model. And I believe I do a linear model. Yeah, I believe that'll work. All right, so I get a pretty cool plot here in that I get the overall scatter plot, and I get factor, well, instructional technique 0, 1, and 2, which I defined previously. And I can see the different, let's kind of scroll in on this just a little bit. I can see the different lines. And again, thinking that now clearly the red slope is different than the blue slope because they cross. But I'm dealing with sample data and I'm making a statement about a larger population. So when I look at this, when I observe this plot, I feel very comfortable in proceeding with assuming that the homogeneity of regression slopes has been, is not violated. Now, we can transition into a p-value approach, and it's kind of a creative approach. We can create an Anova model with our y predicted from our covariate and our independent variable, plus the interaction of our, get the right, yeah, plus the interaction of our independent variable and our covariate. All right. Now, I'll want to run this, and I want to be able to use the Anova command because I want to run a type 3 sum of squares Anova here calculation. So remember, for Anova, I need to install car or access the library for car. I've already installed the package. And now I want to run Anova HORS, and I want the type to be 3. Now, again, I'm not running the Anova or the ANCOVA design just yet. This is still under the heading of checking for homogeneity of regression slopes. So when I run this with the interaction, I have tunnel vision on the interaction term. So if we have statistical significance, I could care less. This stuff up here in in this part of the analysis, I could care less about this. It doesn't tell me anything. I have tunnel vision on the interaction. And if I have statistical significance for the interaction, then the homogeneity of regression slope assumption is violated. If I have do not have statistical significance, as I have in this situation, in this case, for this example, then the homogeneity of regression slopes is not violated. So I will proceed assuming the homogeneity of regression slopes assumption is not violated. All right. All right, the next thing I want to check is I want to check the independence of the covariate and the treatment groups. And what this means is these two aren't related. So the mean covariate, so across the treatment groups, I want to be not statistically significant. So I'm just going to create a model here. Should be pretty clear what I'm going to do if I don't want the means to vary of the covariate across treatment groups. I'm just going to run an Anova of the covariate across the treatment groups. What's going on here? Groups. Oh, clumsy today. All right, so I run the model. I do not have statistical significance, so I will proceed with the assumption that we do not violate the independence assumption between the covariate and the treatment group. All right. So we've checked all the boxes. We've gone through the traditional Anova assumptions, and we've tested the two assumptions that are specific to ANCOVA. Again, that the predictor, that the covariate and the independent variable are not related, and the homogeneity of regression slopes. Next thing I want to do is I want to dive into the effect size. No, I don't either. Let me back up a little bit. All right, so I want to proceed with a few issues that we run into in calculating ANCOVAs with R. Well, it turns out to calculate an ANCOVA is very, very, very simple. So again, what is the goal of this study? We want to examine mean final exam scores over instructional method when controlling for the covariate. All right, and really it's not really controlling for, it's when we adjust for. So we're going to adjust the variance when assuming that the covariate is included. So examine mean final exam scores over instructional unit when adjusting for the variance for the covariate, when including the covariate. Now, the ANCOVA design is, so let's just call it our ANCOVA. We use the AOV command. Our dependent variable here is final exam. We want to put in our independent variable first, and then we want to add our covariate. Now, watch what happens, as you probably would expect. If I run this model and use summary ANCOVA versus this model, where I put my covariate first, and then enter in notice that I get slightly different results. In fact, it actually turns out to be quite different. The p-value for the independent variable in the second model is 0.81, and the p-value is 0.4 in the first. Now, again, this goes back to an issue that we have with R. R uses a type 1 sum of squares calculation method by default, which is a sequential calculation method. So sequential means it, in this case, we entered the independent variable first, taking into account the independent variable. What does adding ACT do to our model? Same thing down here, entering the covariate first, and just taking into account that it's there, okay? What does adding this factor, the independent variable x, what does it add to the model? Well, that drives some people kind of wacky. Okay, remark. What's a way that we could that we could take care of this? One way is to get better. I'll get an error. Is to use the type 3 sum of squares. So if I come up here, you'll notice that I get exactly the same thing. So that's one method. But what I think I want you to do, and this is really where I'm going to be able to detect who is listening. It reminds me, I probably shouldn't call him out, but one of my least favorite students who I like as a person, he was just a least favorite student for me because he just would not allow me to teach him anything. He wouldn't watch my instructional videos. If something came up, he would go online and come up with some of this wacky stuff. I just really got frustrated with him because he wouldn't allow me to teach him anything. I don't know what was going on with it. It doesn't matter. But so allowing me to teach you something, if you circle back to the previous video, I made a very subtle, well, actually not so subtle, um, hint, remark, a bit of maybe advice, if you will. I want you to think about ANOVA as what is at the end of the video. I want you to think about ANCOVA. I want you to think about a base ANOVA. What happens to the base ANOVA when we add in the covariate? So it should be pretty clear which one of these techniques I want you to do. What I want you to perform. I want you to perform this one, because this takes the ANOVA design right there and then adds in the effect of the covariate, given that the independent variable, in this case, instructional delivery method, is already in the model. So this is what I expect you to report, and it's what I'll expect you to report when you conduct your master's thesis with me.